Hello everyone, this is Group 10. I'm Zhengchen Song. My teammates are Jinran Xie, Qingluo, and Wenhao Gu. Our topic is about firmware verification of security critical hardware and firmware interactions in commercial SoCs. First of all, let's introduce some keywords. Firstly, firmware. Firmware is a special kind of software that provides low-level control for the device and is written in some memory device. For example, BIOS chips is a typical kind of firmware. Then let's talk about firmware verification. Firmware verification is an act to prove or disprove the correctness of the system's algorithms. It uses some mathematical tools to do that. So although automated tools has highly developed nowadays, but manual review is still very important in security evaluations in SoCs. This is because automated verification tools are often defeated by some strange security bugs that only by manual reasoning we can find these bugs. But manual review is not enough because it's harder to repeat and people are easily to make mistakes in this method. So automated tools are needed. There are some preliminary research on this topic. We can divide them into two categories. First category is that we can compare firmware into software and we can analyze it in hardware in a hardware level, but it's too detailed for commercial SoCs, so it will cost a lot to do that. The second method is to abstract hardware as software. Then we can analyze it as a software verification problem. This approach only retains the firmware visible architecture, so it's cheap and easier. So in this paper, we are focused on the topic that use software verification tools and model checking approach to find bugs in security critical models such as boot rooms. This kind of bugs if we find this kind of bug post-production, it will cost a lot for the chip manufacturers. We use the method model checking in our paper. This is a method that we use some mathematical tools to express this system as some logical formulas. Then we traverse this model to find if there is any bugs in the system, but it has post-capability. So we should find some, we should develop some automated tools to do that. So let's let Wenhao to tell you more details about this paper.
Yeah. Hi everyone. So what's SoC? SoC is system on chip whose components always include CPU, memory, and I/O ports, and secondary storage, which are all on a single substrate or microchip. As shown in Figure 1, it is a typical system on chip architecture. And this figure in our homework floor, we can see all the modules are connected with the bus. So here's the table of various security flows in commercial SoCs and their verification strategy. As we can see, flow 1 to 4 is purely hardware implementation. and are verified using hardware-only verification techniques such as RTL simulation, FPGA-based emulation. And Flow 5 has purely firmware implementation, and this type of properties are verified using firmware-only verification techniques such as static and dynamic code analysis tools. Flow 6 and 7 can be implemented either using purely hardware mechanism or using purely firmware mechanism. So hardware-only verification or firmware-only verification are used. However, they don't directly apply to security flows that involve hardware-firmware interactions. And flow 8 to 12 in table belong to hardware firmware interaction. Effective verification methodology for such properties is an open and active area of research, which is also the key point of our presentation. We present our methodology and experiments on formally verifying the security flow 10 to 12. Before we introduce the methodology of verification, here's are some terms of hardware firmware interactions in bootloaders. First of all, what's a bootloader? SoC bootloaders contain a chain of loaders with each one verifying the integrity and authenticity of the next. This creates a chain of trust which stems from an immutable root of trust. And this immutable root of trust is the boot ROM. As the core in the SoC is powered on, it executes the immutable boot code that is stored in the boot ROM. So as we can see, the bootloader job is to bridge the boot ROM, the gap of the boot ROM and the user applications. As we know, boot code are stored in boot ROM, and what is primary task of the boot code? It includes 3 points. The first one is configuration register locking. A boot code helps to read system security configuration from the fuses and initializing the SoC by writing and locking configuration value into numerous registers, and these registers are called configuration registers. This implementation corresponds to trusted firmware locks sensitive registers before execution of untrusted firmware. The second task is to control transfer to PBL. Loading the primary bootloader either from the external flash or from the I/O channel to the on-chip RAM. And this implementation corresponds to correct image is selected based on boot configuration. And the third task is to support test mode boot. And this allow for chip manufacturer debug during the early boot stage. And this implementation corresponds to authorized users cannot access more debug capabilities than allowed. And Qin will introduce the verification methodology.
Okay, the first step of the methodology is source level modeling and verification. All firmware modules in case study are written in C code, and all the hardware behavior it captured relevant to our flows are C subroutines. The software abstraction is not required to be cycle accurate or be precise for proving the security properties under consideration. This results in significant improvement in both modeling and verification efficiency compared to hardware-based approaches. The hardware-firmware interactions considered in this paper rely heavily on MMIO write operations. which stands for Memory Mapped Input-Output. The software modeling thus captures firmware visible functional behavior of pertinent MMIO write operations and their side effects. The MMIO uses the same address space to address both memory and I/O devices. The memory and registers of the I/O devices are mapped to address values. So when an address is accessed by the CPU, it may refer to a portion of physical RAM, or it can instead refer to memory of the I/O device. Thus, the CPU instructions used to access the memory can also be used for accessing devices. Next is verification framework and engines. The high-level security properties are broken down to assertions at the source code level. All hardware and firmware interactions are replaced by software abstraction models, and assertions are compiled into an intermediate representation using LLVM compiler framework. The resulting code is then analyzed with SMAC model checker. Any scalable model checker that supports verification of multi-threaded C code can be used for our purpose. So LLVM stands for low-level virtual machine. It is a set of compiler and toolchain technology which can be used to develop a front end for any programming language and a back end for any instruction set architecture. LLVM is designed around a language-independent intermediate representation that serves as a portable, high-level assembly language that can be optimized with a variety of transformations over multiple passes. And the SMAC toolchain provides a modular and extensible software verification ecosystem that decouples the front-end source language details from back-end verification algorithms. It achieves that by translating from the LLVM compiler intermediate representation into the Boolean intermediate verification language. Last is the verification flow. The verification flow begins with the given C code for firmware, RTL for hardware, and supporting documents, such as security architecture specification, register description. We analyze the hardware and firmware interaction under verification and its security objective. We then construct a software model of the underlying hardware using property-specific abstraction. And the software model is composed with the firmware, and the security objective is translated into assertions, which are inserted in the composed model. And last, the assertions are then verified using a software model checker. Then Junyan will introduce the verification results.
Okay, so now I'm gonna talk about the security flow verification results of flow 10, flow 11 to, I'm sorry. So let's just do on this slide. Now I'm gonna talk about a security property of flow 10, flow 11, and flow 12 from table 1, and the security flow verification results for each of the flows. First, I'm gonna talk about the security flow verification results of test boot mode. As we all know, certain SoCs offers two boot modes, normal boot mode and test boot mode. In test boot mode, an authorized user can get full control of the system and run test code to boot the system. To avoid insider attacks, we use a watchdog timer to ensure the system is restarted after the test code execution ends. In other words, if execution of the user-supplied test code ends before the watchdog timer expires, operation of the whole system should expire. And that's the security property of test boot mode. The verification results shows that a system enters normal execution after user test code completes that's a bug, and they can also be manually confirmed. Then, for the property of security flow verification. As we all know, register lock is a hardware access control mechanism using lock bit to protect target bit. The target bit can be written only when the lock bit is in recite state. So the security property of register locks is we need to make sure sensitive configuration registers are properly locked, which means the respective locking functions are always called. The result exposes some bypassing locking functions, but it's not considered as a bug due to the reachability property. And finally, I want to show the security property of the signature verification flow. The boot ROM uses a deeply nested decision tree. The boot ROM uses a deeply nested decision tree to call the appropriate function for image execution. And we need to ensure the decision tree, the selection logic of the decision tree is correct. For example, the bootloaders from the local storage at the end and the I/O interface can be executed at the same time. The verification result can quickly find out a trace target to target call site, and it doesn't imply any bug. As we cited before, this paper presents a low-cost methodology for formally verifying security properties of various hardware-to-firmware interactions. Although our model checking are based on simple incorrections, but it still reflects formal verification has strong potential in verifying the security property of hardware-to-firmware interactions in the future. And that's all of our presentation. Thank you so much for listening.